So our optics unit kind of has three big topics: reflection, refraction, and lenses. So in this video, I'll be covering everything in reflection and refraction. I'll make a lenses video once we've gotten to that point in the unit. But yeah, optics is the study of light and how light behaves. And you've probably heard the day-old saying that light behaves like a particle and a wave. So geometric optics looks at how does light behave when you model it like a particle, right? When you have light rays, which we kind of model as like, you could think of as like flowing photons, right? Of the flow of these particles and how they behave. And then physical optics is, well, how does light behave like an electromagnetic wave? This unit is geometric optics. Our next unit will look at, well, how does light behave like an electromagnetic wave? So the most basic understanding of geometric optics is that, well, when you have a light ray that's from coming from a light source like the sun or whatever, the sun emits light rays in all sorts of directions. But if you do have a light ray that ends up hitting some sort of surface, right, then that light will reflect, and that light will reflect according to the law of reflection. So if you think about the law of reflection, let me draw a little bit of a better surface. The law of reflection really just says, hey, if you have a surface, and if you were to draw what we call a normal line. Now, normal means perpendicular, right? If you think about normal force, that's a force exerted by a surface perpendicular to the surface. So the normal line is perpendicular to the surface, and this angle measured from the normal, we call it the angle of incidence. I don't know why that took me a second. Angle of incidence. That angle of incidence will equal the angle of reflection when measured from the normal, right? This is a pretty basic law, and this idea that the angles will end up being the same hopefully kind of makes intuitive sense, right? If you have, let's say you have light coming right into the normal, the angle of incidence is 0, right? Because it's right on the normal. So the angle of reflection is also going to be 0. It's going to bounce right back. If you're coming in at a really shallow angle, well, then it's going to reflect like at a shallow angle. The angle itself would be large, right? Because, when you're measuring it from the normal, but it would have like the same, I guess, steepness, right? Like it doesn't randomly get steeper. It reflects at that same angle. That's the angle of reflection. And it's responsible for why we see things, right? This, I know I'm a nerd. I'm not this much of a nerd. I don't know how to solve this thing, but this Rubik's Cube, right? Like whatever light's bouncing off of it, it's coming into my eyes, and that allows me to see this Rubik's Cube. And if you have a really perfectly smooth surface like a mirror, that means all the light, right? Because it's so smooth, all the light would reflect perfectly, and you get to see yourself, right? And we'll talk about mirrors more in a second, but what I'm getting at is that, well, in reality, most objects that reflect light, like the Rubik's Cube, like, this marker, like me, we have a bunch of imperfections, and thus we can't really reflect light perfectly. If you were to take this Rubik's Cube, right? If you were to take like a Rubik's Cube, this is what it looks like, maybe at a kind of at a macroscopic level when you're just looking at it. But when you zoom into the surface, right? If I were to zoom into this little piece right here, it is super bumpy. And sorry for my dad laughing. It's really bumpy. It's not perfect. There's all sorts of little imperfections. So when light bounces off of it, if you were to zoom into this bump, it's kind of like a mountain. So if you were to zoom in even further, light hitting here, that normal line, it's going to kind of reflect it like that. And if you have a normal line here, if this is your normal line at this point of the surface, then light will kind of bounce, and all the normal lines are random. You get like the light kind of scatters. Like it's still reflection, it's just not perfect reflection. You don't get to see, like, this isn't a mirror, right? Like this you just see as an object. You're seeing the imperfections. You're not seeing yourself. A mirror is when it's perfectly smooth, right? Ideally, right? Like, ideally, the mirror is perfectly smooth and it reflects all of the light kind of uniformly. Because the normal line at any single point on this mirror will always be perfectly parallel to the ground or whatever. So that's how you get virtual images, right? If you look at a mirror, the light bouncing off your leg from whatever source. Oh, this marker's terrible. Let me get this marker. The light bouncing at your leg will it'll reflect off by the law of reflection and hit your eye. And because this light right here is hitting the mirror and reflecting back, your eye can't see this light ray, right? Like, it's only seeing whatever light ray is coming directly into the eye, but it creates almost this illusion that the light actually is coming from behind the mirror, right? Our brains literally perceive this reflected light as coming behind the mirror, as kind of, I guess I don't know much about neuroscience, or I don't even know if this is a neuroscience. I don't know what neuroscience is, to be honest. Point is, like, I don't really understand why our brains does this, but my guess is, like, our brain kind of has to be like, well, where is this light coming from? It has to come from behind because light doesn't bend. In our brains, that we like, it's an illusion. The light looks like it's coming from behind. So this light would create a virtual image because of that false light that's converging behind us. That's creating a virtual image. So if this is my foot right here, then that's where the foot would appear right there. And let's say this light, right? If you had this light and coming from the other foot, right, it would kind of look like this, right? It would hit it at a different angle so that it hits our eyes. Or I guess I should say, remember, the light goes in all directions. I'm drawing the path that leads to our eye, but it would create a virtual image then right here. So you can see they got swapped, right? Whatever is closest to the mirror appears closest to the mirror. Or I guess in other words, like, it's swapped the feet, right? This foot right now shows up on the right, and now here it shows up on the left. Just like how a real mirror would. So that's basically the basics of a plane mirror, right? This is a virtual image being created, and it would look reflected. And you can use some geometry and some you can use geometry to prove that whatever image you see would be equidistant to your location from the mirror, right? The image distance is going to equal the object distance from the mirror. Well, for a plane mirror, that's all fine and dandy, but for curved mirrors, that sort of object distance equals the image distance. That's not always true. And that comes into the world of spherical mirrors, convex and concave mirrors. So convex and concave mirrors, I always think of it as like a cave. So a concave mirror, right? It's like it's caving in. So it's going to kind of look like that. I guess a convex mirror is going to have the same shape, right? But a concave mirror is when the mirror is on the inner edge, I guess, and then a convex is on like the outer edge. So if we were to draw kind of some light rays, let's draw a light ray. How about this? Let's draw a light ray coming in like so. So you might be saying, well, does this follow the law of reflection, right? What will the reflected angle be in comparison to the the incident ray? Well, the deal is, yeah, it will follow the law of reflection, because if you take this mirror and you kind of like take this piece of the mirror right here and zoom it in, if you zoom in that piece of the mirror, like really, if you get really close into it, if you got a microscope or something, I don't know, if you zoomed into this part of the mirror, it is basically straight, right? It's gonna look essentially straight. And it's going to look like there's a normal line like right there. And, you know, this will probably make sense. Like this whole idea of zooming in and finding that normal line right there, that's very akin to just calculus in general, right? And finding tangents and normals to like a curve. It's the same idea. If you zoom in, it looks basically straight. So we can say that there's a normal, like that is normal to that plane right there, that kind of plane that we zoomed in on. So you can see this angle would be the angle of incidence. The law of reflection still follows. We would get an angle of reflection that is similar to that. So that's the deal with like the law of reflection, right? It still holds with curved surfaces. You just kind of have to zoom in, and that's how you would, you know, kind of justify that it works, right? If you zoom in, and you know that's why it works here. So a spherical mirror has a pretty cool property. If you take the center of curvature, right? So if you take the center of curvature, which is, I just said the same thing twice, whatever. Center of curvature, if you imagine this thing completing a full circle, center of curvature is just the center of that circle. Half that distance from the center to the mirror, which is really just a radius, right? Half of that you would find, at half that distance, you would find the focus point. So the focus point is where all the light that comes in parallel to this line, we call it the principal axis. It's like the line that connects the focus and the center and the mirror. Any light that's coming in parallel, you could see, I guess the focus would really be right there, right? All light bouncing off would hit the focus in some way, shape, or form. Whether you have, I guess, yeah, it would hit the focus. And that's important because that means, that means a couple of things. First of all, if you know that it hits the focus, you can draw a ray diagram for really any kind of a scenario. I'm not going to dive too much into like ray diagrams in this video. It would take too long. But the whole point is that, you know, you can draw a person, I don't know, like an arrow, and you can take a look. Well, light from the top of this arrow, it would bounce and hit the focus. Some of the light will just go directly into the focus and bounce, and then light coming into the focus and then bouncing off like so, right? Light coming parallel to the ground and then bouncing into the focus, and then light coming from the focus bounces parallel back. And you can see the light will converge, and then also you can get a third ray for the center. The light will converge right here. So that's how you can kind of figure out that, hey, for a convex mirror, when you're still past the focus, it'll be upside down, right? Because you will see how the light converges, and that's a real image. This image that you see in a convex mirror, that is like a physical light converging at that spot, and your brain processing that as an image, right? That's real light at that point. At the focus, if you stand at the focus, well, the closer you get to the focus, the more like zoomed in everything looks in. You're gonna look bigger and bigger and bigger and bigger, and it's gonna look really weird because you're also gonna appear farther away. It's kind of trippy, honestly, if you were to slowly zoom in. But at the focus, standing at the focus, you don't get an image because there's light won't converge at any point, right? If you're standing at the focus, then you know, light bouncing here from your head would just bounce into the focus, but then light that would be bouncing from your head into the focus, that just goes like straight down. Like it just goes straight down like so. If I were to draw this a little bit better, light would be going straight down like so. There'd be light going like this, but then at the focus you would have light going straight down. It doesn't converge at any point except like right at your feet. And if you have like a bunch of rays, you're gonna imagine that, yeah, that light just won't converge at any point where you can see an image. It won't create an image. So at the focus, it won't create an image. And then if you stand like, let me get a new mirror. This is kind of just disgusting. If I stand like within the focal diameter, right? Like within the mirror and the focus, then I can't really see a real image at this point because any light that converges will be behind me. If I'm standing within the focal diameter, I can't see behind me, which then would be an interesting question. I just thought of in my head, but I won't say it just not to confuse you guys. Whatever. If you're standing right here and you're facing the mirror, you're not gonna see. You're not really gonna see like. You're not really gonna see like a real image, right? Any light would just converge behind you, like so. But what you would get is a virtual image. You can imagine light that, if you think about light, you could have light coming from the focus, kind of like so. And you can have light kind of trailing through the focus like so. The light converging backwards would create the virtual image of you kind of standing behind the mirror, and you would get a virtual image. So that's kind of the deal with that. For a convex mirror, you would never see a real image, right? The reason why you don't see a real image when you're past the focal diameter for a concave mirror is because the light will converge behind you. You can't, in other words, you can't see the light converging. You can only see the light seeming to converge behind the mirror. That's a virtual image. But for a convex mirror, yeah, you won't see a real image because the light won't converge, right? Any light that is hitting the like the mirror, it will diverge kind of away. So any image you do see in a convex mirror is going to be a virtual image. And it follows very similarly for a concave mirror, like in terms of how the light reflects. So if you think about the focus in the center, if you think about, so this is the focus, and this is the center. So if you think about any light that's seeming to hit the focus, right, that would seem to hit the focus, it just ends up getting reflected away. Any light that's going straight into the mirror would seem to reflect away from a focus, like so. So the light would diverge like so. And you can draw your ray diagrams very similarly. It's just now you're dealing with rays that seem to converge behind. And, you know, you can draw your ray diagrams like that. Let me know if you were interested in me making a video on ray diagrams. I can, I have a video on ray diagrams, so maybe you can check that out. So that's mirrors. The last main thing with reflection is understanding the mirror equation. You can mathematically relate the object distance and the image distance of what you would see with one of these mirrors using an equation. And that equation is the reciprocal of the object distance plus the reciprocal of the image distance is going to equal the reciprocal of the focal distance. And this equation hopefully is pretty similar, or simple, not similar. Similar to what, right? It's simple. Hopefully it's simple. If you know the object distance and you know the focal diameter, you can pretty easily find the image distance. And that's kind of the idea with the mirror equation. There are really interesting ways that they can ask to you. So like there's really interesting questions they can ask. So like in the packet, there's a worksheet, and they ask some pretty cool questions, I think. Like concave makeup mirror is designed so that the virtual image is twice the size of the object when the distance between the object and the mirror is 15 centimeters. So what it's really saying is that, okay, when the object distance is 15 centimeters, the virtual image will look twice as large. Which brings us to magnification. Magnification's honestly, I think, more simple than sometimes it can seem to be. Magnification is really, so the magnification is the ratio between the image distance versus the object distance. So if your image distance, like the distance that it seems to appear from the mirror, if that's larger than your object distance, you get a bigger than 1 magnification. What does that mean? Well, it means that things look bigger, because that means whatever your distances are in terms of the image, they appear larger than whatever the actual object distances are. It's like a ratio, right? So this ratio ends up also equaling like the height of the object, height of the image versus to the height of the object, right? Like these distances, they are magnified in such a way so that they share a common ratio, which is equal to the magnification. So if your magnification is 2, which is just that question saying, right, is that you look twice as big. And what was the question asking? I think the question was asking, what is the focal diameter? It's page 17. It's saying you're gonna determine the radius of the curvature. Well, if you're so it says virtual image, right? So if you're standing, oh my god, wait, these markers are so terrible, makes me want to cry. So if you're standing so that you see a virtual image, right, then you're gonna obviously have kind of like a virtual image like so, and then you would have the light would bounce like that, and then you would also have light kind of like that. Okay, so if you have your that means your passive focal distance. That's one good thing to note, because you see a virtual image. So if the magnification is twice, that means when S object is 15, that means when S object is 15, your S image, right, the distance for the image, it's not just going to be 30, it's going to be negative 30, because you see it past the mirror. So it's like this side the distances are positive, this side the distances are negative, and 1 over 15 minus 1 over 30, well, that's, 1 over 15 is 2/30. So you get 1/30. That means this 1 over focal distance is going to equal 1 over 30. So if the focal distance is 30 centimeters or whatever, then the center of curvature is going to be 60 centimeters, because it's twice that, so it's going to be 60. So there are really like kind of weird ways they can ask that, but they all just force you to use this equation to figure out what you need. That's basically reflection in a nutshell. Now let's talk about refraction. So hopefully this video isn't too long. Let me see how long is, if it's hopefully at least, okay, 23, that's not bad. That's not bad at all. Let's talk about refraction. So here's the deal with refraction, right? Light can reflect, just bouncing off the material, but it can also bend, and it bends for a really peculiar reason. Let's say you have light, it's an electromagnetic wave, and obviously this unit's dealing with rays rather than waves, but you know, light doesn't need a medium to travel through, because it's an electromagnetic wave. And electromagnetic waves are literally created, we'll probably talk about this more in the next unit, but they're created through the oscillation of charged particles, which oscillate the electric field and magnetic field, and you get those electromagnetic waves. So you don't really need a medium for those electromagnetic waves to travel through, right? It's just changing electric and magnetic fields. They don't need a medium. So if light is passing through a medium, you know, it's probably gonna start slowing down, right? And we can model this slowing down of a material, right? We can mathematically model this as a certain ratio. We can say, I'm going to use a black marker, we can say that the speed at which light travels through a certain medium is going to equal the speed of light in a vacuum, c, which is 3 times 10 to the 8th meters per second, over a variable called n. Or we can express this as the ratio n between c and the v in a certain medium. N is what we call the index of refraction. So if n is bigger, then the speed of light in that medium is going to be slower. In other words, or I guess also to note is that n will always be at least greater than 1, because the ratio between the speed of light in a vacuum to a certain medium is always going to be greater than 1. Speed of light in a vacuum will always be the fastest. And you can study special relativity to learn more about that. Point is, this is what we call the index of refraction for a material. It is unitless, right? Because meters per second of no units will lead you to meters per second. It has no units because it's like a ratio, and we call it the index of refraction for a material. And refraction, right? That word, it means to bend. Well, why does light bend when passing through two materials? Let's look at it like this. Let's say you're a runner, and in pavement you run the fastest. So you're trying to go from point A to point B, and let's say in pavement you run like 10 meters per second, right? You're pretty stinking fast. How do you get from point A to point B in the shortest amount of time? Well, no duh, you kind of just go straight, right? If you're going at that constant speed, any other path you take will just result in unnecessary waste of time. The path that leads to the shortest time is a simple diagonal, right? Straight line. Well, here's the deal. In mud, you don't run as fast. Let's say in mud, let's say you run 2 meters per second. You run like considerably shorter, or slower, not shorter. So let's say this is the line that separates pavement from mud. So this all here is mud, and this over here is air. So for a situation like this, you know, if you want to take this route of least time, right? If you're trying to like get to from point A to point B in the shortest amount of time, you might not actually want to take this path, because now you're spending a long time going 2 meters per second in mud, and then you're taking a really short amount of time, or like you're spending like a short distance where you can run the fastest. I wrote air. I'm so sorry. This should be pavement. Ideally, if you want to get here to in the shortest amount of time, you would spend more time running, on pavement, right? You want to spend most of your time going at 10 meters per second versus 2 meters per second. So you're pretty clever. You're like, well, instead of just taking this path, how about I spend a short distance kind of in the mud, and then I can spend a long distance at 10 meters per second in the pavement, right? So this is 10 meters per second and this is 2 meters per second. You know, you're traveling more distance, but on average, you're going to be running faster. You can get there in less time. Believe it or not, light actually operates on this very principle. It's called Fermat's principle. Fermat's principle tells us light takes, from point A to point B, it'll always take the path of least time. So, for example, if you have light going from, let's say we have light that's going from water to air, right? Going from water to air. If you have a light ray coming in at a certain angle of incidence, right, like so, in water, then it will refract, the light will bend away from the normal. and it'll have a larger angle of refraction. Why? Well, it's the same principle here. You can see it even makes like a pretty similar path. If light is going from a slow medium to a fast medium, it bends away from the normal. Versus if, let's say, we switch this to like pavement, or I wrote the water, but let's say we switch this to pavement and then to mud. Well, now you want to spend more time in the pavement, so you would rather take a path like this. And I kind of overshot it there, but hopefully you get the idea. You would take a path like this, spending more distance in the material that you're faster, or the pavement, or whatever, right? Where you can run the fastest. So if you're going from air to water, well, the light will bend toward the normal, like so. And you can see it even makes a pretty similar path. So that's how light that's why I guess it refracts. It's due to Fermat's principle. But how much will it refract, right? Air has an index of refraction of 1, and water has an index of refraction of about 4/3. So how exactly will these angles end up being, right? Based off the index of refractions, we call that Snell's law. Snell's law literally derives from this principle. If you know calculus, you can try to minimize the amount of time you take in a certain material and get this equation. The equation is that n1 times sine theta 1 is going to equal n2 times sine theta 2. So index of refraction 1 multiplied by the sine of the angle of incidence will equal the index of refraction 2 times the sine of the angle of refraction. So this is what we call Snell's law. And if you know, it's a classic. If you know 3 of the variables, you can find the 4th, right? This equation I don't think is too hard. Just remember to do inverse sine, right? If you want to find theta 1, theta 1 is not equal to, right? It's not equal to n2 sine theta 2 over n1, right? This is not true. Instead, you just got to do the sine theta 1 is, right? Instead. So you just got to do the inverse trig, and your angle of incidence or whatever is going to equal sine inverse n2 sine theta 2 over n1. So just remember to do your sines, inverse sines, and all that stuff. Should be a pretty simple equation. Let's talk about critical angle. Critical angle occurs when you're going from a slow medium to a fast medium. As we kind of noticed, if you're going from water to air, the light bends away from the normal. Well, guess what? Eventually, if you make this angle bigger, then the angle of refraction will only get larger, right? Because it's bending away. And eventually you get to a point, a certain critical angle, where the light entering in is going to bend 90 degrees away. And you won't see light really entering this new medium at all. Instead, the light at that point will completely reflect, and according to the law of reflection. And this is called the critical angle. So the critical angle occurs at that angle when the light will bend at an angle of incidence or refraction of 90 degrees, and you just get reflection from that point on, right? Like you just get light can't even leave that medium; it just reflects back. Which is pretty interesting. And we call this total internal reflection, and it's a pretty cool phenomenon, and it explains why diamonds are sparkly. Using that thing we did in the worksheet, right? The angle of incidence of diamond, the angle of incidence of, wait, did I say angle? I'm so sorry. The index of incidence, I just said angle of incidence. Oh my god. Index of refraction for diamond is about 2.4. It's pretty high. And if you were to take a look at Snell's law, when does the angle of incidence occur, or the critical angle occur? It occurs when theta of refraction is 90, or in other words, sine theta 2 is 1, because sine 90 is 1. So you get sine theta 1, or I'll call sine theta c, right? The critical angle will equal n2 over n1, or theta c will equal sine inverse n2 over n1, where n1 is the slower medium, right? Because you're exiting from n1 into n2. And because n1 is 2.4, right, that's pretty high compared to 1. It would be 1 over 2.4. That critical angle will be pretty small. It'll be like 24 degrees. And because of that, diamonds, if you take a look, let me kind of show this to you guys. If you kind of see like these angles right here, any light entering from the top, it will make an angle larger than 24 degrees, right? Like that, that angle of reflection will almost always, I think geometrically, it will always be greater than the critical angle. So that light at the bottom will always reflect. If your angle of incidence is less than 24, then light will leak through the bottom. It'll refract back into the air. And that's how you know if a diamond isn't cut well or if it isn't real. If it isn't cut well, then they messed up the angle so that light entering from the top, it won't always be larger than 24 degrees, right? Because they have to cut it. They have to use some math and some geometry to be like, okay, if you have light entering from the top, how much do we have to cut it so that light will always be at the critical angle or larger in terms of like reflecting at the bottom? If the index of refraction isn't 2.4, it's not diamond, and it'll probably be lower than that, like maybe like glass or something, I don't know. And then light will it will start refracting down into the bottom, right? It won't reflect because your critical angle is larger than 24 degrees. It's not a real diamond. Or it's just, if the critical angle isn't 24 degrees, it can't be diamond, right? Because it depends on the index of refractions. That's reflection and refraction in about, 40 minutes or so. Hopefully, hopefully this is somewhat helpful. I'm making this for my friend because she hates paying attention in class, and she just would rather make me make these videos. All right, thank you, bye. Thanks for watching.